Hi everyone, welcome back to my Z80 computer series. I'm going to be continuing on with the prototype keypad that I've been building. Some good news, as you can see, circuit boards have arrived from JLC PCB as always. Really surprised by these. They took 12 days from placing my order for them to manufacture them, international shipping over from China to the UK and delivered to my door all within 12 days. I think that's really impressive. I do have some spares. If anyone's interested in them, if you're in the UK, let me know. I'm not sure that I'll give them all away, but just let me know if you're interested. You can see over here I have soldered on all of the diodes. I don't think I've explained what the diodes are for yet, but we'll have a look at the circuit diagram in a moment. I've also soldered on a header. I don't know if I'm going to regret that, because I have a feeling it's not going to fit. So what I could do is I could solder this now onto the back of this panel, and I have tried it. It does fit. I believe it would work with no problems, but I'm not going to do that because I don't like this red panel, although I do really like the red panel, but I don't think it really suits the colour of the keyboard. So what I've been busy doing is actually designing a case for this, and again I'm not sure if this is all going to fit together, so we'll find out. Basically it consists of a back and a front with a cutout in it that will fit over the key switches. The idea is they'll sit in there like that. From a side profile it should sit something like that. So you kind of get the idea. I don't like the red showing through, so I printed a new plate. I printed it in black. So that will fit in here. I believe it will go in that way. Now I suppose technically I could have made that as one single piece, but I think it would have been a little tricky. It goes that way actually. Would have been a little tricky with regards to support, so I think it is easier just to print them in two separate pieces. I'm intending to screw them together, little fixing holes here. There's 4 of them. I'm hoping the screw heads are not going to be too close to the edge of the case. Yeah, that will fit in there. The keys should snap in. We should be able to solder the circuit board on the back, and then there is a back piece to it. Just drop that out for a minute. So just 2 halves to it will screw together. There are holes all the way through the back piece. You can see just in the corners here. So a screw will go all the way through that, and then screws in the top half. The holes in the top half only go about halfway through. So that should screw together. Again, hoping the screws will fit. I forgot to countersink them, and I think I've put them a little bit too close to the corners. So a few regrets on this case. I've got a feeling this case is not going to 100% fit. But that's what prototyping is all about, really. You need to try things out. That's why I've done a small one rather than doing a full-size keyboard straight away, because almost certainly I'm going to have regrets. Now, I also wish that I'd made it sort of angled. It should really have sloped upwards so that the keys have a little bit of an angle on them, but I've not done that. So maybe we'll have a Mark II at some point that will be angled. And the biggest thing I'm worried about is I'm not sure that this plug on the back here I'm not sure the case is deep enough to accept it. I have put a little slot in here, so the ribbon cable from this connector will go through that slot. But again, I think everything is just all too tight, because I think that's going to sit right up tight against that, and there probably just won't be room. You can sort of see the connector right behind that slot. Almost certainly not going to be room. So probably going to have to make another one. But I'm going to have a go at putting it together. We'll see what problems we've got, and then we'll have to probably make a Mark II. So I think what I need to do is remove all these keycaps get all the switches out, get them transferred over to this plate. So I do have a keycap puller, so let's give this a go. Okay. So like I said, I've already soldered the diodes. I think it is important to do them first before you attach it onto this part. So what I'm going to do, as I solder them on, I'm just going to make sure that each switch is firmly pressed through the PCB. In theory, if they're all nice and tight up against the PCB, then everything should be straight. Just looking at the clearance of things. The plate does seem to be sagging down in the corners. I'm not sure why. Should in theory all pull straight when I screw it in. Yeah, so it was a nice fit. Just a case of soldering that on there now. Soldered all the switches on. I guess I can replace the keycaps. I think I'm going to put the number lock key on here instead of the escape key. Nice. And this should fit on here like this. So I'm going to have to find some screws to go in the back here. The only thing I'm worried about is if the switches are a little too close to the edges, they might catch on the edges. Looks like I've left it a bit close. So it has worked out quite nicely. I did have to file the plastic away a little bit around the edges because it was just touching the key switches, but not much, just a little bit. And now they clear the edges, so they're operating without catching, which is nice. So if I made another one, I just want to leave a fraction of a millimetre, maybe 0.2 of a millimetre all the way around the edge, just for a little bit of extra clearance. This plug has worked out quite nicely, but it doesn't quite fit in the case. So let's explain how this keypad is going to work. We'll start by looking at the physical hardware, and then we'll move on to looking at the software program. If we look at our input switches that we've used previously, the onboard tactile switches, you can see that we've got a single row of 8 switches, and we're actually using a pull-up resistor that pulls the lines high, and then when we activate each switch they get pulled down to ground, taking one of the lines low. And then we have our buffer here that isolates us from the data bus unless we actually want to do the reading. So we can say that these switches are active low. When the switch is activated, the signal goes low. And if you remember, the buffer chip here is activated via these lines here, which I've got tied together. And on the previous diagram, I was just taking these through an OR gate, and I was looking at the IO request line and the read request line, and when they both go low, this chip would be activated. Now if we look in comparison to our switch matrix, what we've got here is several rows of switches, and I've actually realized I've made a mistake here in the way I've orientated my diodes. Because I've got the diodes pointing in this direction, and if you remember, the diodes are there to stop the signals from going back through a switch down to a different row. Because I've got the diodes orientated this way around, I've designed it in such a way I'm expecting high signals to come in through the rows and go through a switch through the diode, and the high signal will appear on the columns here. So that means that these switches are actually active high. When the switch is closed, the high signal is going to appear on the columns. So what I've done is I've introduced a second input buffer here. So we've got our original buffer for the onboard key switches, and then I've introduced a new keyboard buffer here, a new input buffer here for our keypad, and we're going to feed this with the columns from the keypad C0 through to C5. I'm only using 5 of the 8 possible data inputs to this chip, so the 2 that I'm not using are just pulled down through the pull down resistors. Now notice the difference here. These switches were active low, so they used a pull up resistor connected to 5 volts. These ones are going to be active high, so they have pull down resistors connected to ground. So yeah, that's a bit of a mistake. I did want to have them active low and use pull ups, so it was exactly the same as this, but I made that mistake when designing the keypad, and I'm just going to go with it. Just shows you really that you can do it either way. You can do active high, active low, use pull-ups, pull-downs, whatever. Doesn't matter. It works either way. The next thing I've introduced is this IO address decoding chip, which is another 74HC138. Now we had one of these for the output IO decoding, so this is a new chip for the input IO decoding. So instead of just having the IO request and read request lines going through an OR gate and activating this buffer here, I've now taken those signals over here, IO request and read request, are now feeding into the enable lines of this IO decoder chip. There is actually a third enable line here, G1 pin 6, and I'm just tying that high. That's an active high signal, so I've tied that one high, and these lines will just only go low when we're doing an IO read So that'll activate this chip on an I/O read, and then this chip will be doing the address decoding. I've got my address lines here, A0, A1 and A2. That gives us 8 possible addresses from 0 through to 8, and I'm using 0 to be this line here, and that will be our onboard switches, and address 1 is this line here, and that will be our keypad. Now I want to turn our attention to the Z80 user manual. We're going to be using this instruction here in R, C, R being one of the registers. I believe we're going to use register A. But something interesting when you use this instruction is the contents of register C are placed on the bottom half, A0 through A7 of the address bus, to select the I/O device. If we look at our diagram, we've got A0, 1 and 2, that's the bottom half of the address bus. So that will be register C. But interestingly, the contents of register B are placed on the top half, A8 through A15 of the address bus at this time. So when we're executing this instruction in R, C, register B is placed on the top half of the address bus. So we're actually going to use that feature. Now, if we look at our keyboard matrix diagram, we've got rows here and columns, but the rows are what I'm trying to draw your attention to. And I've got my connector here. This is my keyboard connector. And you see rows are connected here, R0, R1 and R2 are our 3 rows, and they're connected to pins 1, 3 and 5. And then if I go back to my trainer board diagram, I've got the same connector here, and on these pins 1, 3 and 5, I've got address lines A8, A9 and A10. They're the first 3 bits of the top half of the address bus. So I'm actually going to use those address lines to feed into the rows of our keyboard matrix. So the address that we set will determine the row that we've activated in our keyboard matrix. Now, if we turn our attention to the software side of things, we'll show you the program that I've written. We have here the main loop, just 3 instructions: call keypad read, call output A, and jump relative to main loop, which is this label up here. So it's just going to keep looping around here, calling the keyboard read, and then calling the output A. Output A actually outputs the contents of register A. So we can actually have a look at that output A here. It's quite simple. You do a push BC just to preserve the contents of registers B and C. Don't really need to do that. I'm just doing it because I want this thing to scale up. Then we're loading C with 0. 0 is this is output address decoding. So this is our output address 0, which is our green 7-segment LEDs. And then we're calling out C, A. So we're just going to output the contents of register A onto those green LEDs. And we're going to pop BC and return. So pretty straightforward, just outputs the contents of register A onto the green LEDs. The more interesting bit is the keypad read. So it's going to enter the routine here at this label, keypad read. Now, before we look at this, I'm just going to draw your attention down to this keypad map down at the bottom. So dB is defined bytes, so I'm just defining some bytes in memory, just some data that I'm putting into memory. Now we've got these numbers here, $1, $2 and $4. These are actually our addresses, the high byte of the address bus. So we're going to load these values into register B, so it appears on the high byte of the address bus. Now, the notation here, I'm using 3 different types of notation. Some of the numbers begin with $1. That's just a hexadecimal notation, so they're hexadecimal numbers. Some of the numbers are just simple digits here, like we've got 1, and we've got 13, and I've got 0. They're just decimal, so they're decimal numbers. And then some of the values I've got in double quotes, like this / here. I notice I've got one there in single quotes. Don't think it matters if you use double quotes or single quotes. They're characters, and they'll just be translated to their ASCII codes. But essentially, they're just numbers. All of these are just numbers that we're storing in memory at this particular location called Keypad map. Now, these numbers here, 1, 2, and 4, are important because they are going to define which row we're driving. If we assign value 0, 1, line A8 will be high because that's the number 1, and A9 will be low and A10 will be low. If we use the number 2, line A9 will be high and 8 and 10 will be low. And if we use the number 4, A10 will be high and 8 and 9 will be low. So we'll either be driving A8, A9 or A10 depending on which of these 3 numbers we're using down here. And then for each of those rows, I've just defined the actual keys that sit in that row. So we've got the /, the star, the minus, the 7 and the 8. The 1 here represents the number lock key. There was no ASCII code for that, so I just arbitrarily assigned it the number 1. There's the second row, 9 plus 4, 5, 6 and 1. And then the third row is 2, 3, 13 is the ASCII code for the enter key. And we've got 0, the decimal point. And then this key is unused. I only have 17 keys and I've defined 18 keys here. So this last one never gets used. So the main principle of operation of this keypad read is to loop over the rows, and then for each row, loop over the columns. And we'll check each column, see if we see a high value in that column, and that means the key is being pressed. And as soon as we find a key being pressed, we just jump out of this whole routine and we load that value into the A register and return. So I'll go over it line by line. So load HL, keypad map. So I'm just starting HL off, pointing at the first byte of the keypad map, which will be the 0, 1. I'm loading D with 3. This is the number of ports or rows to check. So the number of rows to check. And then load C, 1. C is always 1 for reading from the keypad. Then we go into read keypad 0. We have load B, HL. Get the keypad port address from the table. So that first byte that we're pointing to here will get loaded into register B. And if you remember, that's register B going onto the high byte of the address bus. And then we're going to inc HL. So we move to the first character here. And then we do an in A, C. So we actually read the whole row in, and it goes into register A. We're ANDing it with $3F because we're only interested in the first 6 bits. We've actually got an 8-bit address bus. We're just ignoring the first 2 bits. And then we're loading E, 6. This is the number of keys in the row. That's going to be our loop counter for looping over the characters in the row, the keys in the row. We then drop into this label, keypad read 1. SRLA is a shift right logical. I think that's what SRL stands for, shift right logical. So we're shifting register A to the right, and bit 0 will drop out of the end and set the carry bit. So the bit we're actually interested in is now sitting in the carry flag. We then can do a check on that carry flag. JRC is jump relative if we're carrying. So if the carry flag is set, we're going to jump relative, and we're going to jump to keypad 2 or read keypad 2. So if the carry flag is set at this point, that means the key is pressed. So we would jump down here, we would load the value into the A register and return. But if we don't find a key, we're going to inc HL. That moves to the next character. And we're going to decrease E, that's our loop counter, so we're decreasing the loop counter. and then we're going to check the 0 flag now to see if we decreased E to 0, which meant we've finished looping around the characters. If we haven't finished, if we're not 0, we're just going to go back up to keypad read 1 and loop around, and we're just going to keep going around and around as we work through all the characters in that row. If we find one, we'll jump out down here. If we don't find one, we'll actually fall through to here, where we'll decrement D, which is our row loop counter. And again, we'll check to see if we've decremented down to 0. If we have, we're finished. If not, we keep looping around. But because we're looping around the rows, we loop back to keypad read 0, which takes us up here to start a new row. We'll keep looping around, and eventually we'll either find a key and we'll jump out via this little bit here, or we'll find that we've scanned all the keys and nothing is being pressed. We'll fall out here, and A will just clear the register A, no key found, so register A will hold 0 and return. So either we return here with A being 0 and no key being pressed, or we'll return here where A actually has the value of the key that was being pressed. I've got my fast clock over here. I've built myself up a more permanent board using the 4060 chip as before, powering that from here with +5 volts and ground, and then I can select the clock speed I want on these yellow connections. I'm using 56 kilohertz. I've turned off both the clocks on the trainer board, so the manual clock and the auto clock are both turned off, and I'm feeding in the clock signal via here. Now it's currently displaying a 0 up here because we're not pressing any keys. If I was to press the numlock key, it should display the number 1, and it does, so that's nice. And then for the other keys, it should display their ASCII codes. So we've got the / is 2F, star 2A, the minus is 2D, the plus is 2B, the enter 0D, and the decimal point 2E. Now for the other keys, 0 through to 9, the ASCII codes for those are 30 through to 39. So we've got 30, 31, 32, 33, 34, 35, 36, 37, 38, and 39. So it's all working really nice. I'm really pleased with that. Took me quite a while to get the whole thing designed and built and up to this stage, but I got there in the end. If you've got any questions on any of this, if there's anything I haven't explained in enough detail, then please ask by leaving a comment. Other than that, thanks for watching, and I'll see you in the next one.